All right, so let's dive into covalent compounds with the knowledge from the ionic ones that we had done before with the dot diagrams and the properties. Covalent and metallic should go a lot faster, a lot easier. To sum up what we had talked about in the very first video about introduction bonding, covalent bonding and covalent bonds are formed between two strong nuclei that have a strong enough attraction that they both end up fighting over those valence electrons. Sometimes we refer to that as sharing, but it's this tug of war between them that ends up binding and holding those two atoms together. And that's what we call a covalent bond. So because they're fighting over them, those valence orbitals, they end up overlapping with each other as those two electrons are in both of the orbitals of the two different atoms. This ends up forming individual molecules rather than a large crystal like in the ionic compounds, because we don't have charges pulling in every direction. We just have the shared overlapping orbitals tying the single molecule to itself. So some examples. First here we have CH4, which is commonly known as methane or natural gas, like you use in your stove if you have a gas stove. It's also what we have in the Bunsen burners in school. CH4 has a single carbon atom bonded to 4 hydrogen atoms, which is what the little 4 there indicates rather than the 4 out in front. Remember, if there was a large number here, that would be indicating that there were 4 of these methane molecules. To make this compound, we have carbon atoms on the left, we have hydrogen atoms on the right. To make methane, we have to recognize that carbon has 4 valence electrons, indicated by its dot diagram with 4 electrons. And based on what we know about the octet rule and filling up that orbital, it's going to gain electrons since it's a nonmetal with its strong attraction. Whereas hydrogen, also a nonmetal, is going to generally gain electrons, but hydrogen can only gain 1. It's an exception to that rule because hydrogen's valence shell is the 1s orbital, and that can only go up to 1s2. They both have a strong attraction relative to each other because carbon, even though it has 6 protons compared to hydrogen's 1, carbon's valence shell is on energy level 2, so it's farther away from the nucleus than the electrons are for the hydrogen. So to make this bond, the carbon atom on the left is going to be attracting and pulling in this valence electron from the hydrogen. But hydrogen, since it is similarly attractive overall, is not going to let go of that electron, and in fact, it's going to be attracting and pulling on an electron from carbon in return. And we see that this was going to have to happen between multiple hydrogen atoms because one hydrogen alone isn't able to give up enough electrons to the carbon. So we're going to have 4 separate instances of electrons needing to be shared. And what this ends up forming is we have carbon here in the center. We have, I'll do those in different colors to make it more apparent. We have carbon with its original electron bonded to one of hydrogens. And we have that in 4 instances all around the carbon, showing the carbon's original electrons here in the blue, and the original electron from the hydrogen in red, to make a molecule that looks like this. This is commonly drawn with lines instead of the dots. So if you've seen this in biology, we have carbon with the 4 hydrogens around the outside. Now, it's also able to bond in other arrangements where we could have carbon, instead of bonding to the 4 hydrogens, carbon could have also bound to a different carbon atom instead. Right? We could have had each of these carbons linked to each other to make a chain or some other shape arrangement, which is why we can have a variety of different compounds between carbon and hydrogen both. We can have acetylene, C2H2. We can make propane, like in your gas stove for a barbecue grill. Right? All of those have various amounts of carbons and hydrogens because it comes down to how these different atoms pair up and bond to each other to share their electrons. This is different from ionic compounds because those formulas are based on the repeating ratio, the repeating pattern of the ions in the crystal, rather than the cohesive molecule itself. A few other quick examples. If we look at chlorine with its 7 valence electrons, do that in a different color, we know that each of those could gain 1 more. So if we have a large container of just chlorine atoms, Because they are so highly attractive, they can actually pull and bond to each other. And what this would make would be two different molecules here in this case of one chlorine bound to another chlorine, and a separate molecule of another chlorine bound to another chlorine. And it's this high attraction between these two atoms like this, which is what causes chlorine to be diatomic. Remember from back when we first labeled our periodic table, there are 7 diatomic elements. They have a strong enough attraction for themselves like this that when they're left alone, they will actually do covalent bonding to themselves. And as a quick reminder, those 7 are hydrogen, oxygen, nitrogen, and then all of the halogens, fluorine, chlorine, bromine, and iodine. As we get into chemical reactions, we're going to have those 7 memorized because we're going to be using them pretty frequently. And one last example here we see with water. Water, we have oxygen where it has 2 missing electrons in terms of its octet. Hydrogen has 1 missing electron on each of those because it's stable with just 2 electrons, making 1s2 as its filled orbital. So if we look at the first oxygen atom, it can share and bond an electron here with the hydrogen. And if we were making water, it can share and bond an electron with another hydrogen, making OH, H, which we commonly write in books with the straight lines like this. And it's these extra electrons up here, which is why we usually write water with a bent shape like this, because it's not a straight line because those extra electrons take up space as well. Now, again, this isn't the only combination that hydrogen and oxygen can bond to each other in. For example, let's take away this drawing really quick. Instead of having the one oxygen bonding to 2 different hydrogen atoms, it's also possible for the oxygen to bond to another oxygen, and then that one to bond to another hydrogen. Right? So again, variety of different possibilities. That second compound would look like this, where we have 2 hydrogens bound to 2 oxygens rather than 2 hydrogens and 1 oxygen. And that second compound is what we call hydrogen peroxide. It's potentially what you put on your cuts when it makes them all nice and fizzy to disinfect the bacteria that may be in there. In terms of properties, vastly different from ionic compounds because they do not have this large crystal structure. Instead, we have this separate, distinct molecules, right, where each of these examples here, oxygen, carbon dioxide, water, ammonium, and methane, each have individual molecules that are separate and distinct from each other. They are not one large unit like the crystals would be. Rather, the force of attraction between them is, remember, what we call an intermolecular force, like in this second diagram down here. Because they're separate, distinct molecules, and they only have these intermolecular forces between them, it's a lot easier to separate one molecule from another molecule, making them boil and melt at much lower temperatures. And in fact, a lot of small covalent compounds are already gaseous or liquids at room temperature because they don't need much energy to separate. For ones that are solid at room temperature, things like plastics and rubber, usually those are formed by taking lots of smaller covalent compounds like this and doing chemical reactions to actually bond and link them to each other, making what are called polymers, which I'm sure you've talked about a little bit in biology as well. For example, starch is a polymer of different sugars. And in comparison to ionic compounds, which were electrical conductors when they're dissolved, covalent compounds don't really readily dissolve in water in the first place, but even if they did, there are no charged particles here. The electrons are not free to move because they are contained within the single molecule. And then that particle itself doesn't have a charge on it. It's not an ion, which means that even in water, when these things are floating around, they're not carrying a charge with them, so there's no electrical conduction. So these make really good electrical conductors. And as we were talking about with water and dissolving, these things don't really readily dissolve at all. The reason for that being is that water can't really grab onto them because water has that polar charge, which is what interacts with the ions. But most covalent compounds aren't polar. If they are, and they're small, water can dissolve them, similar to sugar. But for non-polar things like oils and fats, water can't dissolve them at all, which is why, for example, a styrofoam cup can hold a bunch of water in it, or coffee or tea or something like that. However, if you used a non-polar solvent, a non-polar liquid, something like acetone, for example, commonly known as nail polish remover, sorry, it can readily dissolve any of those non-polar covalent compounds. For example, if you tried to put acetone into a styrofoam cup, you would notice that your styrofoam cup quickly dissolves into a pile of goop, like this on the bottom right corner here. So if you actually have that at home, you can easily try that, or check out the link here on the bottom by going into the slides on the Google Classroom page, because it is actually pretty interesting to watch how quickly this styrofoam cup just dissolves completely into a pile of little plastic. If you did try this out, you can actually shape and mold this plastic into something, and then when all the acetone evaporates, you have a nice hard plastic model as a result. But this is why, for example, even with nail polish, and why nail polish remover is made out of this, water can't dissolve the nail polish compounds because they're non-polar, but acetone can readily take them off. And in comparison to the ionic compounds, we already mentioned this before, but they readily boil and melt at much lower temperatures compared to things like ionic compounds that have the charges pulling them together. Right, so cesium and bromine would be an example of an ionic compound, and cesium's a metal. Both of these two would be examples of covalent compounds with no metals present.